a big fan of the lead going as we expect it to go. All right.
I need to do this for myself.
And she says there's a but there's actually not.
Okay, so I promised you that I would tell you why it is that we say sometimes ion-ion attraction is larger than ion dipole, and sometimes ion-ion attraction is smaller. So here we got our crystal lattice of salt, and again, it forms a crystal lattice, quick review, because the sodium ion is positive, the chlorine ion is negative, and they just stick, right? Positives attract negatives, negatives attract positives. There they go. And then the sodiums attract a bunch of chlorines, the chlorines attract a bunch of sodiums, and we get a crystal lattice that looks something like this. So far, so good? Now, water molecules come along. If you remember, your water molecules have a partial negative around the oxygen and a partial positive around the hydrogen. It's like do, 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 and the partial positives grab onto the negative ion, surround it, and tear it from the lattice. And then the partial negatives come around, surround the positive ion, and tear it from the lattice. And if there's not enough magnets, that's what happens. There we go. There we go. We'll get that one later. Okay. So what had to happen? The water molecule had to apply a force against the ions. The ions were pulling towards each other, and they were resisting the force that the water molecule was pulling on. So it comes down to this. If here we go. The attraction of the ions is given by how much charge they are and how small they are, how charge dense they are. So this is a cool formula. It's called Coulomb's law. There is no math in Coulomb's law for this class. We just need to know how an equation works. So if, first of all, this is the attraction, the electrostatic attraction the ions have for each other. K is a constant. Q is the charge of the first thing, sodium's +1. Q2 is the charge of the second thing, chlorine's -1. And then D is the distance between their centers, like from here to here. Are you with me so far?
Yes.
So you look at the ionic attraction, and we can actually mathematically calculate it. Here we're going to qualitatively discuss it. If Q1 and Q2 are +1 and -1, and D, the denominator, is a certain number, that's going to produce a force. If we have a +1 and -1 with a larger distance between the ions, when we make the denominator larger, what happens to the number it represents? Gets smaller. That's super important. Again, math. When the denominator is larger, the number it represents is smaller. So if you look at these two crystal lattices, they're about the same size. This one's sodium fluoride. This one's magnesium oxide. Ions are pretty close. And obviously, the oxygen's bigger because it has 2 more electrons. Magnesium is much smaller because it's +2. But how would you compare the force holding the ions together with sodium fluoride with magnesium oxide? Take 30 seconds to chat with your neighbor. Which of these two is going to have the stronger ion-ion attraction? Come here, you chlorine.
Smaller.
Okay, so let's do this. If you think magnesium oxide is stronger, do this. If you think magnesium oxide is weaker, do this. And if you think they're the same, do this. Stronger, 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 stronger. Yeah, because they're about the same distance apart, but magnesium has a +2, so Q1 is 2. Oxygen has a -2, so Q2 is 2. So this one has more ion-ion attraction. If that makes sense to you, give me a thumbs up. Wait, question.
What did you mean that it's 2?
Because the Q1 is the charge of the positive thing, +2, and the Q2 is the charge of the negative thing, minus 2. In sodium fluoride, Q1 is 1, Q2 is 1, so this is 2, 2, this is 1, 1. Question?
So would the numerator always be negative because one of the charges? Or do the negatives not matter?
Yes. Something you learn in physics is a negative force is an attractive force. So like when opposites attract, you have a positive and negative that are attracted to each other. So yes, if we did the math, F would be negative, and that means it's an attractive force. But we're not going to do any math. All we care about is magnitudes. Okay, which makes sense that if you put sodium fluoride on a hot plate, crank it up, it's going to melt. Molten salt's a lot of fun to play with. Really dangerous, but a lot of fun. If you put magnesium oxide on a hot plate and crank it up, it's just going to laugh at you. Because when you melt something, you cause these to get rearranged. They go everywhere. Similarly, if I put sodium fluoride in water, does it dissolve?
Yes.
Yes, because the water molecules can break the electrostatic force. If you put magnesium oxide in water, does it dissolve? No, because the water molecules don't have enough strength to overcome the crystal lattice. And in general, it works like this. +1, -1 ions, water will attack them and successfully break their crystal lattice. Anything besides +1, -1, in general, water molecules will not be able to pull it apart. We call those insoluble. Questions? All right, let's just, here we go. Okay, so which compound would have the higher boiling or melting point? In other words, which one is going to take more energy to overcome their forces? Sodium chloride or rubidium iodide? Take 20 seconds, chat with your neighbor. Which one do you think it is? Sodium chloride or rubidium iodide, which one's going to require more heat to melt? If you think it's sodium chloride, point that way. If you think it's rubidium iodide, point that way. Okay, what do you think? Is sodium chloride going to require more energy, or is rubidium iodide going to require more energy? These are both +1, -1. +1, -1, +1, -1. But this distance is that big. That big. This distance is that big. Larger denominator means it represents a smaller number. This one's going to require a lot less heat to make the ions fall apart. Because larger distance, larger denominator, smaller number represents. Is that clear?
Yes.
Okay, if you're comfortable with this, give me a thumbs up. Any part of this seems uncomfortable, wave your hand around. All right, take a look. Lithium fluoride, beryllium oxide. Which of these two is going to require more energy to melt? Is it going to be beryllium oxide or lithium fluoride? It's going to become beryllium oxide, exactly. So they're about the same size, that distance and that distance. But this is +2, -2. So Q1 is 2, Q2 is 2. F is going to be a lot larger. A larger numerator means a larger number. So it's going to require a lot more energy to melt this than melt this. Question?
So how many, like, if it's a 2 negative or 2 positive, does that matter more than the distance?
Yeah, by quite a bit. It's like, yeah, by quite a bit. 4 times more it will be. If there's 3, it's like 9 times more. Yeah. So we only use distance in this class when they're both +1, -1 or +2, -2. We don't mix the concepts. And even in AP, they don't. They don't bother mixing the concepts because the math is like, I know you can punch numbers into a calculator. What I care about is do you understand what the formula says? All right. So again, what it boils down to is a soluble salt is one that is not held very strongly together and water molecules can tear it apart. And what we say is the ion-ion intermolecular force is smaller than the ion-dipole intermolecular force of the water molecules. So this is the ions attracted to ions, holding the lattice together. This is the water molecules attracted to the ions, tearing the lattice apart. If the water is stronger than the ions, we say it is soluble. It will dissolve. On the other hand, when it's the other way around, if the ions are holding together too strongly, water molecules cannot break them apart. We say it is insoluble. Now, there's a bunch of nuance that you'll learn in college, but we don't deal with nuance here. We deal with absolutes. Like, I heard it online. It was like this way. It's like, yeah, it is, but we're not going to learn it that way. Okay, so take a look at these 4 sets of compounds. Should pop up here momentarily. There they are. Take a look at these and decide with your neighbor, take a minute or two, decide with your neighbor which of these things are likely to dissolve in water.
Sodium chloride and chem.
Does anyone have any questions about these?
No.
Okay, so if you think it's going to dissolve, give me a yeah. If you don't think it's going to dissolve, give me a no. Okay, KF.
Yes.
Does it dissolve or no?
So,
It will dissolve. +1, -1. Water's going to tear it apart. Copper sulfide.
no.
No. +2, -2. There's enough attraction, water can't pull them apart. Aluminum nitride.
No.
Definitely not.
Very no, right? +3, -3. Lots of attraction. Water can bang at it all day. It's not going to do anything. Cesium bromide.
Yes.
Yes. +1, -1. Water will attack it. It will dissolve. And we talked about yes and yes. Questions? If you are comfortable with everything you said, you're ready to work, or everything I said, and you're ready to work on your own, give me a thumbs up. If you have any questions at all, wave your hand around. All right. So there's a matching worksheet and skills test on this, and you are welcome to use the time to do that thing.